So we're beginning to look into the world of surveys and learning about surveys and population and samples. And we live in a world today where we're given a lot of results of a survey taken on any news that we look at. We might hear perhaps 35% of a certain population based on a survey sample is reacting a certain way to a certain product. Um, and we want to look at this carefully. So we're going to spend a little time learning about this. Um, we're going to first learn how to distinguish between population and samples, identify possible parameter in statistics. Notice population and samples go together, parameter and statistics go together. Identifying possible sources of bias in surveys, and identifying features of a simple random sample. Let's begin by looking at some definitions. A population is a group of objects or people we study. We want to study, not with to study. This is a typo right here. We want to study. Okay? Stared at it and wondered why it looked that way. A population is a group of objects or people we want to study, and a parameter is a numerical value that characterizes some aspect of the population. So, population and then a parameter is a numerical value that characterizes, okay, numerical value that characterizes some aspect of the population. We're going to get into more details on this in a second. So I'll continue this. Now, populations and parameters. Here's an example. Data is gathered on the heights of all NBA basketball players. The mean of this data is calculated. So the population that we're looking at is all NBA basketball players. The numerical part of this, the parameter, is the mean height of all NBA basketball players. Now, measuring populations. We're currently in the United States involved in a census where families received information in the mail on how they can participate in the census of the United States to determine the current population. So a census is a survey which measures every member of the population. So if everybody truthfully fills out the information required in the census, then we would have a measure of every member of the populations. Most populations are too large for a census, so we study populations by measuring samples instead. Now, I'm going to get into this whole idea of samples instead, okay? A sample is a collection of objects or people taken from the population of interest. Now, the numerical part, a statistic is the numerical characteristic of the sample. I hope you're seeing where this is going. For the population itself, the numerical part is the parameter. For the for the sample, the statistic is the numerical part of it. Because a statistic is used to estimate the value of a population characteristic, it is sometimes called an estimator. Okay? It's used to give you an idea of what is occurring in the entire population. For example, if we say that the population of the United States is 400 million, and we want to study part of that population by taking out a sample, we would take out a sample of, say, 20,000 people and study them instead as representative of the entire population of the United States. Now, we have to be really careful that the 20%, the 20,000 that we take out is actually representative of the population, and we didn't pull it from, say, the western United States or the eastern United States, and that we pulled it from all over the United States to get a representative sample. Statistical inference is the art and science of drawing conclusions about a population based on observing characteristics of a sample. It involves uncertainty because the entire population is not being measured. An important component of statistical inference is measuring our uncertainty about that. Um, and I just wanted to speak first about how we designate the different types of parameters and statistics. In general, Greek characteristics are used to represent population parameters, and English letters. So Greek characteristics are used to represent population, and English letters are used to represent statistics. Easy to remember it that way. So a sample mean which is statistic, is represented by the English letter X bar. A population mean, which is a parameter, represented by the Greek letter mu. And we have different designations here. For example, standard deviation for statistic is S, sample variance is S squared, sample proportion is P hat. And in parameters, when we're talking about population standard deviation is sigma. Population variance is sigma 2, and population proportion is simply designated as P. Notice the difference here. Sample proportion is P hat. Population proportion is designated as P. This is going to come back later when we calculate standard error. Now let's talk about bias and the meaning of bias. So a survey method is biased if it has a tendency to produce an untrue value. There are three types of bias: measurement bias, sampling bias, and use of an estimator that is biased. Measurement bias results from asking questions that do not produce a true answer. occurs when the measurements tend to record values larger or smaller than the true value. For example, asking people, how much do you weigh, it is likely that people will report a number less than their actual weight, resulting in an estimate that tends to be too small, because they're asking the wrong question when they ask, or they're not asking a question that would generate a true answer. This results in an estimate that tends to be too small. And remember, when we're talking about a sample, we're talking about an estimate, a statistic that is estimated. Sampling bias occurs when a sample is used that is not representative of population. And this is very popular in our world today. For example, internet polls, people who answer these polls tend to be those who have strong feelings about the results and are not necessarily representative of the population. For example, if we're polling people who say tend to prefer one political candidate, and the people who usually take these polls are people who tend to have strong feelings about the results, and they really don't represent the entire population of most of us who do not have strong feelings about, say, a particular political candidate. And a process called simple random sampling, SRS, is used to draw objects at random from the population without replacement. Big deal here, without replacement. A random sample is one in which every member of the population is equally likely to be chosen for the sample. Equally likely. Everybody has an equal chance of being selected for the sample. Now, listen carefully here. A true random sample is difficult to achieve. Statisticians have developed methods to produce random samples that can be used to estimate the characteristics of populations. Unfortunately, the people who take samples, for example, for a new system, tend to take samples from population that suit their interest and not necessarily get a random sample from a given population of people. So chapter 7.2 goes into a little more detail. It goes on how to measure the quality of a survey, how to use accuracy and precision to measure the quality of a survey, and how to describe the important features of a sampling distribution, including standard error. Evaluating surveys. Statisticians evaluate the method used for the survey. The method used for the survey, not the outcome of a single survey. For example, if a group of researchers were survey 100 randomly selected people, we would expect the results to vary from the sample to sample, okay? Because we would want to know how the group did as a whole. We evaluate the estimation methods and not the individual estimates. If we were to take several samples out of this group of 1,000 randomly selected people. Now, the goal is accuracy and precision. An estimation method, a sampling method, should be both accurate and precise. Accurate is the method that measures method measures what it is intended to measure, correctly estimates the population parameter, okay, that the results were accurate. Now, precise is if the method is repeated, we would get exactly the same estimate. If we use the same method a second time or a third time, it would produce estimates that are very, very close and similar to each other. Here's an example. If the goal is to get the golf ball into the hole, okay, which of these pictures show both a method of accurate, precise, and both? So let's look at the explanation for this. This first picture, because all of the balls are close to the hole, shows both accuracy and precision. The second picture shows precision because all of the balls are grouped together on the right, but it's not accurate. It's not where it's supposed to be. And the third picture shows accuracy, but not precision, okay? In other words, the balls are randomly scattered around the hole, but they're not precisely at the hole. Makes a little bit of sense? Okay. Notes about simulation. Our estimator p hat is not always the same as our parameter p. The mean sampling distribution is 25%, the same as the value p. This indicates that the estimator p is unbiased. Even though p is not always equal to p hat is not always equal to p, the estimate is never more than 25% of points away from p. We'll see how this works in a little bit, okay? Now, standard error. Let's look at the definition of standard error. The standard error is the standard deviation of the sampling distribution. It measures how much an estimator typically varies from sample to sample. When the standard error is small, we say the estimator is precise. And I'm going to show you that in the homework. Now, there is a formula that is used that you will need. The bias p hat is 0. The standard error of p hat is given by this formula. The square root of p, not p hat, into 1 minus p divided by n. If the following conditions are met: the sample is randomly selected from the population of interest, and if the sample is without replacement, the population must be at least 10 times larger than the sample size. Okay, those two have to be consistent before we can calculate standard error. All right, let's look at some of the homework questions. Some of the definition questions I'm not going to answer for you. I'm going to do maybe random ones. Explain the difference between a parameter and a statistic. So remember that a parameter is a measure of the population, a statistic is a measure of the sample. Explain the difference between a sample and a census. Every 10 years, the U.S. Census Bureau takes a census. What does that mean? What this means is the census is a survey of every member of the population. So I'm looking through the answers here. And the only one that reflects a census is a survey of every member of the population is measured is answer A. Let's read the rest of it. A sample is a collection of people or objects taken from the population of interest. When the U.S. Census Bureau takes a census, it conducts a survey of all people living in the U.S. Okay? This answer here, based on the sentence, is the most accurate. The census is a survey in which every member of the population is measured. And if you go back to my definition, you will see that. Um, so this is a definition question that came directly from our notes here. Going back up here where we spoke about census. A census is a survey in which which measures every member of the population. And from this particular question in the homework, the only answer that reflects that answer is answer choice B. Answer choice A. Sorry. All right, I'm going to answer this one for you as well, which represents a parameter in which a statistic. So recall that Greek is used for population and English letters are used for statistics. The mean is the English letter. The mean of all students in your school, you survey 30 students. If you're taking a sample of the population, then you would use the English or X bar. Okay, you survey 30 of the students, which means you're not surveying the entire population. More examples. The mean GPA of all 7,000 students at a college is 2.37. And then out of that, a sample of 200 GPAs is 2.68. So hopefully we can answer this question here. Here we're given the population mean is mu, and the statistic mean is 2.68. So that statistics mean would be X bar. Okay, I don't know which one of the answers it is. You can figure that out, yeah? All right, now you need to select a random sample of 3 from 9 friends who participate in a survey. Assume that the friends are numbered 1, 2, 3, 4, 5, 6, 7, 8, and 9. Select 3 friends using the first row. The first row, very important, in the random table. So we're going to use this row here. This row 1. Read off each digit, skipping any digit not assigned to one of the friends. The sampling is without replacement, meaning you cannot select the same person twice. So looking carefully here, as we move from left to right, we have 37330. So the first number that we come up to from 1 to 9 is 3. Then we come up to 7. Okay. Then we see 3 is repeated, so we can't write it again. Keep going down, and we come up to the next column here, and we see 8 is the next number. So 378. Now, for example, if the sample had asked about the second row, going from left to right, we would see from the second row that we have 462. And the third row, so pay attention to what the question is asking. The third row, from left to right, 652. The first 3 that you come up to. All right, now we're going to look at um, how to make these tables using information that we have, okay? So make two given, what is wrong with this thing? All right, let's see if I can get it to stabilize a little bit. Okay, here we go. Okay, here we go. Make two given tables into one table by combining men for capital punishment into one group and men opposing it in another group. So below we have the table that came uh, from the problem. Okay. The student who collected the data could have made the results misleading by trying persuasion more often on one generation than on the other. But she did not do this. Okay, so the survey then, as far as we're concerned, was unbiased. She used persuasion on 10 of the 20 women, 50%, and 15 of the out of the 30 men, 50% also. In other words, the persuasion was used equally on both men and women. Make the two-way table described in the problem statement. For capital punishment, the total for men is equal to 7 plus 13, which is equal to 20. So that's our first part of the table. And for capital punishment for women, uh, equal to 4 plus 4, which is 8. Okay. Then against capital punishment, let's use a different color, 8 plus 2, which is 10 for men. And for women, it is 6 plus 6, which is 12. Notice that the column for men adds up to 30, which matches what we have here. And the column for women add up to 20, which matches what we have up here. What percentage of the men support capital punishment and what percentage of the women support it? Of the 30 men sampled, 20 support capital punishment. So 20 out of 30, which is 0.667 or 66.7%. And of the 20 women, we have 8 out of 20 supporting capital punishment. 8 out of 20 is of 2 into 8, 4. 4 into 8 is 2. Out of 5, which is 40%. Okay? 2 out of 5. Now, on the basis of this results, if you were on trial for murder and did not want to suffer capital punishment, would you want men or women on your jury? So I would definitely, since women have a lower percentage here, I would definitely prefer women, as the percentage of them who are not in favor. So women have a higher percentage, okay, higher percentage. 40% is of women prefer the death penalty, and 67% of men support capital punishment. So that means that more women are not in favor. Okay, 60% are not in favor, 40% are in favor. Okay, so be careful how you answer this. Higher percentage of them are not in favor. It's asking the opposite. So be careful, be very, very careful when you answer this question. All right, I'm going to leave the definition questions for you, and I'm moving straight to perhaps question 10. When a method is called biased, and that's also a definition question. When a method is called biased, it also produces an untrue value. Sorry, not always. Tendency to produce an untrue value. All right, here we go. So, let's look to see if we understand the difference between precision and accuracy here. If a rifleman's gun sight is adjusted incorrectly, this is similar to the golf ball problem in the notes. He might shoot bullets consistently 2 feet to the left of the bullseye target. Consistently close to 2 feet of the left of the bullseye target. Okay? Draw a sketch of the target with the bullet holes. So if he's shooting mostly to the left consistently, this would be what we're looking at. And this shows a lack of bias. Okay? He's consistently shooting to the left because the sight is incorrectly adjusted. So all of the bullets are grouped to the left of the bullseye. Now, if the shots are both unbiased and precise, everything would be directly at the center. Okay? Easy question. According to a candy company, packages of certain candy contain 24% orange candies. Suppose we examine a sample of 250 random candies. What value should you expect for the sample percentage of the orange candy? So we would expect that the sample has the same percentage as the whole population of candy, 24%. Okay, don't expect otherwise. Now, the standard error is computed by the formula. Standard error is equal to square root p into 1 minus p over n. So p in this case is the population, which is 24%, or 0.24 as a decimal, and n is the number in the sample, 250. So you would go to your calculator with this. Second, square root, alpha y equals, to get the fraction bar, 0.24 open parenthesis 1 minus 0.24 close parenthesis. And then on the denominator, we type in the population of 250. And press enter. And this gives us our answer here. 0.27. We're going to capture this screen. Okay, so the standard error is, and they want 3 decimal places, so 0.027. So if we multiply this by 100, okay, we would have 0.027 times 100 gives us, times 100, sorry, gives us 2.7. So we would expect 24% orange candies, give or take 2.7%. That would be the standard error for this particular group. Okay, 24% orange candies, and that sample might be off by 2.7%. 24 minus 2.7 or 24 plus 2.7. It will be close to 24%. Okay, here we go. Population of college students is taking an advanced math class. In the class, there are 3 juniors and 2 seniors. Using the numbers 1, 2, and 3 to represent juniors, and 4 and 5 to represent seniors. Sample without replacement. Draw a sample of 2 people 4 times, once in each parts A, B, C, and D, and then fill in the table below. So for part A, use the first line from the given random number table to select your sample of 2. Note that the selections are underlined. So if we go from left to right here, the number 1 occurs first, then 2 occurs second, okay? We're selecting a sample of 2. So we have 1 and 2, which is both juniors, okay? So they're asking about the percentage of seniors. So if both are juniors, 1 and 2, both juniors, that means there's 0 seniors. Okay, so 0 out of 2 is 0%. Part B, same, now we're using, again, to select sample of 2, we come up to the first 2 numbers we come up to here are 2 and 4. And here we have 1 junior and 1 senior. So this means that in this sample of 2 people, we have 1 out of 2 seniors, which is 50%. Part C. So the first number we come to 3. The second number we come to is 5. So we've got 1 junior and 5 is a senior, so 1 senior. So percentage of seniors is 1 out of 2, which is 50%. All right, let's see what we have here. use the last line again to find a sample of 2. So the first one we come up to is 5 out of from 1 to 5, and then we come up to 4. Okay, 7, 6, 7, 0, 9, 0 are not in the sample. So for part D, we've got 2 seniors. So 2 out of 2, which is 100%. 100% seniors in the sample of 2. Okay, in the sample of 2. So we can actually make up this table now, fill in the rest of the table below showing the results of the 4 samples. Okay, 1 second here. I need to pause this to do something. Okay, moving on here. So they've given us a pretty good idea. Let's look at how they analyze this line. The population proportion of seniors population. Now we have 2 out of from 1, 2, 3, 4, 5. We've got 2 seniors in every group of 5. Okay, so 2 out of 5, which is 40% or 0.4. And then p hat of seniors that we got from the part A answer is 0 seniors. The error is p hat minus p. So 0 minus 0.4 is negative 0.4. From part B, okay, population of seniors again is 0.4. We don't need to recalculate that. And actually that number would be same for all of these, wouldn't it? Yeah. Population of seniors doesn't change. There's 2 seniors in every group of 5. Then we go to the answer from part B, which is 0.5. So p hat minus p is 0.5 minus 0.4, which is 0.1. Then from part C, we also have 50%. So p hat is the same as from part B, 0.1. And part 4, from part D, we have 100%. So as a decimal, this is 1. So this is 1 minus 0.4, which is equal to 0.6. Okay, we had to take part B for this one, 100%. And remember, use it as a percentage, okay? As a decimal, not a percentage. Don't put 0.4 minus 100. You're going to get the problem wrong then. The remaining 3 questions in this homework are definition question. For example, number 14 is asking to measure the quality of a survey's statisticians evaluate which of the following. So if you're measuring, remember I gave you 3 criteria, 1 being the method. When samples are taken from a population and computing the proportion of each sample, which of the following values is always the same? Okay, remember the population proportion doesn't change. And standard deviation, hopefully remember, is the same as saying standard error. All right, that's pretty much all I have for you right now.